Every nation that's a coastal state has some region of the seafloor that falls within their territorial waters, and many countries, including the US, the area that's underwater exceeds the area that's above water. So huge amounts of nations, areas, and regions are just really unexplored, uncharacterized. We don't really know what's there.
We know less about our seabed than we do about the surface of the Moon or Mars. Only 20% of it has been mapped. A map of the seafloor could lead to all kinds of discoveries, like new marine species and rare earth minerals like cobalt that we need for electric cars and mobile phones. The value of all the gold deposits alone on the seafloor is estimated to be around $150 trillion. A map could also help us when tragedy strikes.
Malaysia Airlines Flight 370 disappeared from radar screens.
Mapping of the ocean floor is being carried out. The problem is that the southern Indian Ocean is just so incredibly huge.
To me, a map is a fundamental piece of understanding of who we are, where things are. Once you understand something, you start to value it more. And when you start to value something, that's when you start to really think about making it healthy and preserving it and keeping it going. A map is the first step. It's the basic understanding that you need to figure out where you are.
Oceans. They cover over 70% of the planet, but most of what lies underneath is a mystery.
The seafloor is a really fascinating landscape. We don't have a lot of data to describe the shape of it in detail, but in places where we do, there are spectacular features. There's meandering channels with all kinds of interesting topography. There are canyons, there are seamounts, mid-ocean ridges, all kinds of things that we see on land that are just basically hidden from us by the water.
As it stands, this is what a map of the seabed looks like. All that black, those are the parts we haven't mapped yet.
At present, most people think that the seafloor is actually mapped because you'll see a world ocean map and you can see some shape of the seafloor, but most of that is based on prediction. Roughly 80% of what you see for the world ocean floor is modeled based on measurements of the sea surface height and a computation based on gravity.
In 2017, the Nippon Foundation and the General Bathymetric Chart of the Oceans, or GEBCO, launched Seabed 2030. It's a collaborative project to collect and collate data ocean-wide and create a complete map of the seafloor by the end of the decade. To do this would take one ship around 350 years at a cost of up to $3 billion. That's why data is harvested by all kinds of vessels, from fishing boats to freighters.
Because there is so little data, it's important that vessels that are capable and willing to acquire data when they're just moving around the ocean do so. So we have a lot of data that's collected during transit. There's a lot of academic requirements to make data publicly available. There's industry data that's starting to become more and more available. There's government data. So there's a lot of different ways that this data is coming in, and it's a really messy and challenging puzzle to put together. But what's exciting is that it's a puzzle to put together.
Since Seabed 2030 launched, the area mapped has risen to 20%, and all the information collected is freely available.
The more data we have collectively and other people can access, the faster the discoveries are made, which really pushes forward our understanding at a faster rate than if you held on to that data and it was only you with that data. Things like machine learning and artificial intelligence are also going to kick in the next decade, because with all this data, they'll be able to make connections that a lot faster than perhaps we would have been able to, which then again feeds our human understanding and also gives us new ideas, new ways of thinking, of exploration.
Until the early 20th century, mapping technology was simple, usually a weight attached to a long rope known as a lead line. After the Titanic sank in 1912, explorers proposed using sound waves to find its hull in the North Atlantic. This led to sonar, the most common technique used for mapping today. Operated by the Schmidt Ocean Institute, the Falco is an 82-meter-long research vessel. equipped with 2 multi-beam sonar systems that have helped Deborah Smith and a team of other marine technicians to map over 1 million square kilometers of the seafloor.
You know, you go from somebody with a rope with some knots to sonar acoustics that is, I call it math magic, but it is incredibly advanced mathematical technology to be able to measure the distance and time of travel of sound on a moving ship. Multibeam mapping works by using sonars. So sonar is taking sound and a measurement of time. So you have a multibeam sonar and it sends out a ping of sound. That sound travels through the water column, hits the seafloor and comes back to the ship, and we measure that time and we're able to calculate the distance. Each individual ping of sound has many, many beams. So it looks like a giant fan across the seafloor, and that fan is moving along the seafloor. So you have many tiny little beams going across, and they're traveling along a track. You can look at that data and look at both the peaks and the valleys and the highs and the lows and sort of create a three-dimensional image of the seafloor. The accuracy of multibeam sonar really depends on the water depth that you're in. Think of it like a flashlight beam, and if you're holding a flashlight and you're shining it on the floor, the closer you get to the floor with your flashlight, the smaller that beam is. If you have 400 of these beams all across, so think of 400 people holding a flashlight, the closer they hold that flashlight to the seafloor, the smaller your beam is, which also means the smaller that you can find information or data about. So it really depends on the depth of the seafloor in order to see how much you can define an object.
This variation in depth means that mapping resolution will range from 100 by 100 meters in shallow waters to 800 by 800 meters in the deepest parts of the ocean, which go down as far as 11,000 meters. Remotely operated vehicles, or ROVs, can then be sent down to investigate seabed features up close.
We've just crossed the 1,000 metre mark. It's 4.6 degrees C, and now we're going to drive the ROV down at a higher rate towards the sea floor.
On a recent mapping expedition, scientists on the Falco discovered a 500 metre tall coral structure in Australia's Great Barrier Reef, the first to be discovered in over 120 years.
A place that is incredibly popular, well visited, well traveled, you know, we're still finding new things. You don't know until you map it. And so until you get that sort of high resolution picture, you don't know the sand waves or the old riverbeds that used to be there or the waterfalls off the side of a volcano that used to be above the surface and now is below the surface. It's a little bit of everything. Think of, let's say, Hawaii or someplace where you see a volcano above the water. Picture that below the water.
I'm really kind of obsessed with the whole concept of scale here. Although we can create 3D models and, you know, kind of come up with these visualizations, it's not the same as that feeling of looking out over this big landscape. But, I mean, I think we'll get there soon with VR and other kinds of technology, but it's really spectacular to think about, especially with the familiarity that some of us have with these features, like what it looks like. We look out at the ocean and it just looks flat, maybe with little bumps. We really don't think about all of this that's underneath, and it's really an amazing landscape that's just hidden from us.
With more than 90% of the ocean deeper than 200 meters, fleets of autonomous vehicles could make the data gathering process faster, cheaper, and safer. And new discoveries might help with exploration of all kinds.
I think the ocean can actually provide us with huge insights as we go out into space as well and look for life and other kinds of life forms. I also think in this next few years we will have a different kind of access to the ocean because of virtual reality and augmented reality, and so that will allow us to sit in our living rooms and really experience what's underwater in a different way and see this different alien planet.